The main objective of this project is to design one combined gas steam power station to produce a total of 500 megawatt of electricity so it can supply to new Lumut naval base and its town with the condition that electric generators are gas and steam driven. As a group of engineers employed by Bunga Raya International Corporation, which consists of Fitri, Nashwin, Anis and Aina, we are required to determine the overall efficiency and backward ratio of the combined power plant by applying the knowledge from chemical engineering Thermodynamics 1. The type of cycle used to model the steam cycle is the ideal reheat-Rankine cycle, and for the gas cycle is the ideal Brayton cycle. This is the schematic diagram for the combined gas steam power cycle. Here is the list of assumptions we made for calculation. We do energy balance at each device to find the right equation for work and heat. This is the energy balance at the turbine. And from the energy balance, the equation above is born and will be used to calculate the total work out from the turbine. Next, we do energy balance at heat exchanger to find equation for heat in. So, this is the equation for heat in into the heat exchanger. The heat in is calculated would be including the heating from heating and reheating process. Not only that, but the energy balance equation can be used to calculate the heat out of the condenser. Since the kinetic energy and potential energy of condenser is zero, thus we can exclude those parameters. Then, we can use the equation above to calculate the Q out of the condenser. To calculate the work in of the pump, the energy balance equation is used. Since the kinetic energy and potential energy of pump is zero, thus we can exclude those parameters. We then use the equation above to calculate the work in of the pump. So, I will pass the next presentation to Nashwin.
By utilizing the assumption and information of the properties from the problem statement, we are able to find the properties of the fluid including the specific volume, specific enthalpy, specific entropy, pressure, temperature of each stream. By referring the data collected and tabulated, work inlet for pump is 30.3 kJ per kg, which can be calculated by using the formula shown in the slide. The work produced by steam turbine can be calculated by summing up delta H3H4 with delta H5H6. Next, the heat out of a condenser is 2159 kJ per kg, which can be computed by finding the difference between H6 and H1. Heat in into the heat exchanger is 3835 kJ per kg, which can be calculated by using the formula shown in the slide above. We set the mass flow rate for the steam to 88.5 kg for main streams. For the streams that were separated by separator, each stream contained 29.5 kg per second of fluid. The rate of heat transfer in the steam cycle can be computed by multiplying the mass flow rate of steam with the heat out of the steam. Thus, the rate of the heat transfer of steam cycle is 339 megawatt. Power in of the pump in the steam cycle is 2674 kilowatt, which can be calculated by multiplying the mass flow rate of the steam with the inlet work of pump. Next, the power in of a compressor in the steam cycle can be computed by finding the difference between the power out of gas turbine and net power out of gas. Thus, inlet power of compressor is 53 megawatt. The net work out from the steam cycle can be computed by finding the difference between work out from turbine and work in pump. The net power out from the steam cycle can be calculated by multiplying the mass flow rate and the net work out from steam cycle. The net power out from the gas cycle is 351 megawatt, as it can be calculated by finding the difference between the net power out of combined cycle and the net power out of the steam cycle.
Next, the heat transfer rate into combined gas steam power cycle is 691 megawatt. It can be calculated by summing up the net power produced from the combined power cycle and the heat transfer rate out of combined power cycle, and then we got 691 milliwatt. Besides, the volume flow rate of the steam in the heater is 0.001191 meter cube per hour. It can be calculated by mass flow rate and the specific volume of heating. Based on this slide, using the information heat of combustion of coal, we managed to find the mass of coal required to power the plant. For a year, on the 365-day basis, the coal required we get is 3633,2100 kg per year. In this slide, we are able to determine the isentropic efficiency, isentropic power, and actual power for each device. And we tabulated the data we got. And using the formula of isentropic efficiency and the information in the table to find the actual power of the devices. And then we get the actual power from the combined cycle is 231 milliwatt, which can be calculated by summing up the actual power from the steam turbine and the actual power out from the gas turbine. And then I will pass the next slide to Muhammad Fitri Hakimi.
Thank you, Aina. So now we proceed with the backwork ratio. Okay, we use this formula, which is power consumed by the compressor divided by the power generated by the gas turbine, and we got the backwork ratio is 0.1316. We use this formula to find the overall efficiency of the combined power cycle, and we got 72.35%. So now, how to improve our actual power? First, we can install one more unit of gas turbine or 4 more steam turbine with more heat supply. And then we have to reduce the irreversibilities, and we also can design the pipeline and the power generation system to accommodate higher mass flow rate. For conclusion, our actual power generated is only 231.9 megawatt instead of 500 megawatt. So some modifications are needed. That's all from us. Thank you.